Today we're talking about lexical semantics. We're going to first talk about this concept of a lexicon, all of the words in a language, and how that's represented in a human brain, and how we also represent it computationally. In particular, we're going to talk about one representation of the lexicon called WordNet, and then how it's used in natural language processing for similarity judgments and the task of word sense disambiguation. So the lexicon is this concept of all of the words in a language. And of course it's very large, and in fact it's not even enumerable, because it's never static and words come and go. And also words change their meaning over time. And even for an individual person, the lexicon isn't static or really well defined, because you learn new words, and sometimes you change your lexicon as you move to a different region and adopt that dialect or slang. And the lexicon has a lot of stuff in it. So one, because the lexicon is used for communication, it needs to encode the sound of words, it needs to encode how words change morphologically. It also needs to represent the written representation, at least for those who have a written language. And it also needs to reflect syntax constraints. So here are two of them. One is subcategorization and selectional restrictions. So these are two terms for the same concept. For example, the word eat can only take direct objects that are considered food, unless the verb eat is being used metaphorically. A weaker version of this is what's called selectional preferences. So for example, when we refer to tea, we say strong tea rather than powerful tea. If you go back to how we were thinking about dependency trees, you can think about it this way. Sometimes the parent of a dependency can restrict the kind of words that can be its children in a dependency tree. So this is why it's called a selectional restriction. In linguistics, people often use the term subcategorization, but it's pretty much referring to the same concept. But what's most important about the lexicon is the representation of meaning, because language is about conveying meaning from my mind to your mind. So the meaning of the word must be in there. And a lot of people argue that because of that, the lexicon should be organized based on meaning. And there's some evidence for this in languages. For example, in Chinese and Japanese, you have these counter words. And so you have different counter words for flat things and round things, and so there's some sort of semantic organization in the lexicon that's reflected with this categorization. There's a large philosophical debate about meaning. There's a whole subfield called semiotics, and we're not going to be talking about that. But one thing that comes out of that is that, for the most part, the words that we use really aren't connected to the meaning in any significant way. So there are some exceptions like onomatopoeia, but for the most part, we choose words that seem to be rather arbitrary. And even the concepts underneath the words aren't fixed or static or universal. So for example, different languages split up the color spectrum in different ways. Different languages use different systems of counting. And so the lexicon is only an imperfect reflection of our concept inventory. How do we actually learn words? It certainly isn't from a dictionary, because dictionaries are a recursive mess, because the definition of a word in a dictionary is itself a bunch of words. So this is an infinite regress problem. How do we actually organize our mental lexicon? Before we tackle that, we need to introduce some terminology. So first, there's this concept of synonymy. Different words have the same meaning. We'll see examples of this in a second, but for example, car and automobile, these are words that refer to the same thing, more or less. Polysemy and homonymy are two distinct concepts, but they're related. So polysemy is when the same word has slightly different meanings, and homonymy is when the same word has completely different meanings. So let's see examples of these. So synonymy, this is relatively straightforward. Beat, hit, strike, shut, close. These all represent the same concept, and there are other examples here. Homonymy are when multiple unrelated meanings are attached to the same word. So for example, bank, the financial institution, and the geographic feature, in most speakers' mind, there's no way that those words are connected. Polysemy is when one word form expresses multiple different related meanings. So for example, table, the thing that you might have in a document, and the geographical feature, the top of a mountain, or the piece of furniture, you can see how they're related. Similarly, base, newspaper, you can certainly come up with examples where the border between homonymy and polysemy isn't so clear. So how do you test if words are actually polysemous, that they're not referring to the same underlying meaning? There's a test called the Zeugma test. And so this is when you form a conjunction with the two senses together. So for example, if you take these three sentences, they all have the verb left in a conjunction. And so in the first case, we have, he left Rome and the bills on the table. That sounds weird, but the other two, he left Rome and later the country, okay. He left the bills and an apple on the table, that's also fine. And so what we're seeing here is that there are two senses, at least, of the word to leave. One is leaving a geographical location, and one is placing an object somewhere. So these seem to be different senses. So there are many ways that you can get polysemy. One way is metonymy, when you're conflating a part and a whole. So for example, if you say the White House has issued a statement or the office isn't answering the phone, it's not that these buildings are doing these things, it's people inside the building. But you're now extending the meaning of office and White House. Another way that you can get lots of different polysemy is through metaphor. So time is money, this is a common metaphor, and that creates basically time metaphors with all of these words that you use with financial instruments. Spending time, investing time, wasting time, etc. And this doesn't even have to be standard metaphors, like time is money, that's fairly universal. You can make up a metaphor on the fly, and this produces polysemy as well. My surgeon is a butcher, this restaurant is a zoo on weekends. So while polysemy is fairly complicated, you might think synonymy is easier for computers to handle, but that isn't always the case. So when you're learning a language, or when you're trying to get a computer to learn a language, and you want it to generate some text, choosing the right word is a hard problem. And few words are truly substitutable for one another in all contexts. There's usually better words to use in a context than others. So we saw the example of strong versus powerful T and powerful versus strong computer. We'll see next week how we handle this problem in machine translation, and what we're going to use is language models that we learned about a couple of weeks ago. What we're going to be talking about in the rest of this class are computational models of word meaning. So how can you figure out when words are highly associated with each other, for example in selectional preference relationships? We're going to be talking about how you can measure for a given word how similar it is to another word. And then finally, we're going to talk about computational lexicons, so attempts to create lexicons that are usable by computers. Okay, so first, computational measures of association. So one way of knowing whether two words are strongly associated with each other or not is computing the pointwise mutual information between those two words. So the pointwise mutual information is based on the relationship between the joint probability of the word and the marginal probabilities of the words. The information theoretical definition of this is the number of bits of information that you've obtained about the probability of x given that you've observed y, or vice versa since this is symmetrical. If the PMI is close to 0, then x and y are independent. However, if the PMI is positive, then seeing one of the words tells you that you're more likely to see the other in this context. So for example, obviously rare first and last names have a high PMI score, so Bette Midler has a high PMI score, video cassette and recorder have a high PMI score, unsalted and butter, these are words that have a high PMI score. And you can tell that this came from a fairly old corpus, since Bette Midler and video cassette recorders aren't so popular anymore. But this is how you can detect computationally when words have high selectional preferences for each other. What if you wanted to measure how similar the meaning of one word is with another word? So the way to do this is to build a word vector containing the words it shares context with. So you have this vector for word X, and in this vector, in each of the positions, you take every other word in your vocabulary and you count up how many times does word X appear with this other word. And so now you have this big vector. And so now you can compare this vector that you have for word X with the vector that you get for word Y, constructed in the same way. And the distance between these guys, so for example using the cosine distance or whatever distance metric you want between vectors, correlates well with human intuitions about how different in meaning these words are. For most of the rest of the day, we're going to be talking about a task called word sense disambiguation. And word sense disambiguation, or WSD, is defined as the task of, given a polysemous word in context, which of its possible meanings is intended. And this is necessary if we want a computerized, unambiguous representation of meaning. And typically the performance of this task is based on recall versus precision. And current state of the art is around 70% precision in recall. So first, let's get a sense of why this is so hard. So let's take an example of the word paper in a bunch of contexts. And so this can refer to a physical sheet of stuff made from trees. It can refer to an entity that publishes a newspaper. It can refer to an article that someone has published. But in order for this task to be well defined, in order to figure out, given a single instance of paper, which meaning is intended, we need to have an inventory of those meanings. And in the natural language processing community, the de facto standard for these inventories of meanings is a resource called WordNet. So let's talk a little bit about WordNet. WordNet was designed as an electronic dictionary that would be machine readable. And so it was started by George Miller and later continued by Christiane Fellbaum at Princeton University. It's included as a part of the Natural Language Toolkit. You can also use it on the web at wordnet.princeton.edu. It includes most of the English nouns, verbs, adjectives, and adverbs, and it's inspired WordNets in about 70 other languages. And the goal behind WordNet was to create a psychologically plausible, machine-readable dictionary that could be used for NLP applications. At the time that WordNet began, existing dictionaries were organized by sound, so alphabetically. WordNet took a different approach, that it was going to organize its lexicon based on meaning. And so the reason that WordNet is called WordNet is that you have words connected by links in a network, thus WordNet, and those links between words represent connections of meaning. And a lot of the inspiration came from psychology research that showed that humans did seem to have connections between semantically related words. People answered the question, do canaries fly, much faster than they answered the question, do canaries have skin? And the hypothesis is that humans organize their mental lexicon based on these inheritance properties. So they only store attributes corresponding to the prototype that has that attribute. So for example, animals have skin and animals have ears, birds fly, asterisk for penguins and the like, and then canaries are a type of bird. So if you ask the question, do canaries have feathers? That's a property of birds, so you only have to go up one level. If you ask, are canaries yellow? That's a property of canaries, so you get a very fast reaction. But if you ask, do canaries have skin? You have to go up quite a few levels in order to retrieve that information. And WordNet partially began as a way to try to answer, could this actually work for an entire language? And could you connect all words in a language in this sort of network structure? And WordNet chose a number of different connections in order to build this network. So for nouns, 3 of the relationships that they chose are hyponymy, meronymy, and synonymy. Let's take a look at some statistics about WordNet. So WordNet has about 100,000 nodes. These nodes are called synsets. These are sets of words that are synonyms, hence synset. And most of them are nouns, but you do have good coverage in the other parts of speech as well. And these are all connected by relationship. So the most common form of relationship in WordNet is called the hypo-hypernym relationship. So hypo going down, hyper going up. And this relates more and less general concepts. So for example, car is a specific kind of vehicle, a convertible is a specific kind of car. This is often called an is-a relationship. So a car is a vehicle, a SUV is a car. And this forms a hierarchy of about 16 levels in WordNet among the nouns. Another relationship in WordNet is the meronym-holonym relationship, which is the part-whole relationship. So for example, an engine has spark plugs, and spark plugs and cylinders are parts of an engine. And you can inherit these features, so a fingernail is a part of a finger, is part of a hand, is part of an arm, is part of a body. And so the logical implication of that is a fingernail is part of an arm, which seems a little odd, but I guess it's true. When you move into different parts of speech, you have different kinds of relationships. So for example, one of the relationships is antonyms among adjectives. And so hot, cold, old, new, high, low, big, small, these are pairs of antonyms. The reason that they chose to organize adjectives using this relationship is because this is often how adjectives are learned by children and language learners. Among verbs, you often have manner or temporal or logical connections between the verb. So for example, troponymy is a X is to Y in some manner relationship. So walking is to move in some manner. Whisper is to talk in some manner. Gobble is to eat in some manner. And this creates trees like communicate, talk, whisper. And then there are other relationships that reflect temporal or logical constraints. So for example, if you divorce, you must have been married. If you snore, you must be sleeping. If I kill you, that would cause you to die. Examples out of WordNet. Look at some examples from WordNet. A cab is a kind of auto, is a kind of motor vehicle, is a kind of vehicle, is a kind of transportation. And if you look at car, a car has a car door, and a car door has a lock and an armrest. The Princeton WordNet in English was manually built. However, other languages didn't have these resources, so other languages either used automatic methods to create WordNets from large corpora, or by translating the English WordNet. So now that we have this resource, WordNet, what are some things that we can do with it? So we'll eventually get back to the task of word disambiguation, but first let's talk about similarity within WordNet. So before we talked about using context vectors to measure word similarity, WordNet instead allows you to measure specific meanings of a word. So for example, if you created a context vector for bank, that would include all of the homonyms of bank. But now that we have WordNet, we can measure specific meanings of bank and the similarity between them. So there are a couple of ways of measuring similarity between senses. This is called the Leacock-Chodorow similarity method. This measures how many edges you have to go from one meaning to another within WordNet. The problem with this is that not all edge lengths are equal. So for example, there's an edge between Scottish Terrier and Terrier. This isn't too big of a distinction, but between, say, mammal and vertebrate, that's a pretty big distinction. And so the solution is to use corpus statistics to figure out how specific concepts are. What we can do is we can define the probability of a concept. And the way that we do this is we take a concept, like mammal, and figure out all the words associated with that concept. So then we take a corpus, and we count up all the times any word that is an example of a mammal appears in that corpus. And then we divide by the total number of words in that corpus. Now, you'll notice that we'll probably double count some things because some words are polysemous. We're going to just hope that that washes out. And so now that we have a large corpus and we create probabilities for each of the concepts within WordNet, now we can define the information content of a concept as the negative log probability of that concept. And so entity, the root node of all of the concepts within the nouns of WordNet, has information content 0. However, dog has a much higher information content because it's far more specific. One way of figuring out how close in meaning two concepts are is to take those two concepts and figure out what node in WordNet subsumes them. For example, for the concept cat and dog, what is the most specific concept such that cat is a X and dog is a X? In this case, the least common subsumer of these two concepts is the concept mammal. However, for wolf and puppy, the least common subsumer of these concepts is canine, more specific. And so what we can do is we can look at the information content of the least common subsumer for two concepts, and the more specific that subsumer is, the more similar these words are. So now that we have an inventory of senses, we can now talk about the word sense disambiguation task in more detail. This is a hard problem. For example, if you take this sentence, I saw a 98-year-old man who still walks and tells jokes, and you count up all of the possible senses for these words in WordNet, you get a very large number of combinations. And so there are two broad categories of methods to do word sense disambiguation: unsupervised and supervised. Unsupervised methods typically require some sort of heuristics, such as, for example, assuming one sense per discourse, that in a given document or in a paragraph you're only going to have a single sense of a word. Or they take advantage of semi-supervised machine learning methods, such as, for example, the Jourowsky algorithm. We won't talk about these techniques in this course. If you want to learn more about it, you can take the follow-on course next semester with Philip Resnik. The supervised approach is what's used most often in research, and the way this works is you take a large corpus, you tag a bunch of sentences, and then you train a classifier. For example, using a maximum entropy classifier like we talked about last week. But the difficulty with these supervised methods, even though they work better than unsupervised methods, is getting the training data. And one big problem is that people don't agree on the sense that's being used in any given context. And even to get relatively high agreement, you need to have very skilled annotators, carefully trained. And where a lot of the research has come in is in designing features that can help you identify what sense is being used in a particular context. And this requires carefully engineering features so that you can figure out which meaning is being used in a context. These include using part-of-speech tags, using what a document is about, using words around the context. And even so, we're only getting around 70% accuracy, which shows that word sense disambiguation is a very hard task. And at this level of accuracy, it really hasn't helped many downstream applications that you might want to use word sense disambiguation for, like information retrieval or machine translation. And one of the big challenges of lexical semantics is to create training data and algorithms that can prove useful to other downstream tasks. So to wrap up, we talked about lexical semantics and how humans and computers can represent meaning. We talked specifically about WordNet, a resource for representing word meaning that's been used for many other applications outside of lexical semantics applications. And we'll talk a little bit more about WordNet similarity in class. And then we also talked about the task of word sense disambiguation. This is one of the classical tasks in computational linguistics and is really one of the greatest unsolved problems. And we'll discuss why it's so hard and where people are making progress with it further in class, and hopefully we'll have a good discussion about that.